Welcome back to the deep dive. Today, we're plunging into something, well, something fascinating and, frankly, a bit unsettling. It touches nearly every piece of software we interact with the integrity of our digital building blocks. We're talking about a recent, really massive supply chain attack that rippled right through the NPM ecosystem.
Yeah.
It struck at the very foundations, of countless applications.
Yeah, and our mission for this deep dive is to really unravel the anatomy of this attack. It was pretty sophisticated. We want to explore not just what happened, but how it operated. And it operated with this, well, unsettling cleverness that kind of blew us away. And most importantly, what are the crucial lessons here for protecting, our digital lives, our assets?
Okay.
At its core, you had compromised developer accounts, infiltration of unbelievably popular open source packages, and this malicious payload, we're calling it a crypto clipper.
A crypto clipper.
And
Okay.
the scale.
Yeah.
Just staggering. We're looking at packages with over 1 billion combined weekly downloads affected. It's a real wake-up call, I think, for the entire tech world.
Okay, let's definitely unpack this. Because the discovery, the way they found this attack, it sounds like something ripped straight out of a techno thriller. It starts with a seemingly innocuous error.
Right. Like, imagine this. Just a cryptic build failure pops up in a totally standard CI/CD pipeline. Nothing too unusual, maybe?
And the error message, it was, well, pretty straightforward, actually. Reference error, fetch is not defined.
Familiar to many developers, right? Usually means checking node versions or something.
Exactly. But this specific case, tracing that error led them somewhere unexpected, to a tiny dependency called error X. And here's the kicker. The project's package-lock.json file, it allowed for version 1.3.2 or newer.
Okay, so it just pulled the latest.
It automatically pulled in 1.3.3. And that version, it had been published literally minutes before the build failed.
Wow. Talk about timing.
Right. So the team digs into this new error
Yeah.
X 1.3.3, and it's just heavily obfuscated code, a total mess.
Typical malware behavior.
But buried deep inside that mess, almost like a secret signature, there was this glaring red flag, a function name. Check Ethereum.
Check Ethereum. Okay, that definitely raises eyebrows.
You think?
And what's truly fascinating here, and this is the chilling what-if part, the build only failed because their specific Node.js environment was kind of old enough that it didn't have a global fetch function available.
Right, which newer versions do.
Exactly. Think about that. In a more modern setup, where fetch is just there, this malware trying to exfiltrate data, it could have just gone completely unnoticed, executed its malicious stuff without a single hiccup.
That's scary. So dumb luck, essentially.
Yeah.
An outdated system accidentally saved them.
Pretty much. It really raises this important question about how our system's specific configurations, sometimes even the outdated parts, can inadvertently become our, last line of defense. It's a stark reminder, isn't it? Security isn't just proactive measures. Sometimes it's just chance.
Okay, so here's where it gets really interesting. Because this wasn't just some, isolated incident affecting one obscure library.
No, not at all.
The attackers, they didn't mess around with niche stuff. They went straight for the jugular. They targeted fundamental core building blocks of the entire JavaScript ecosystem. The whole thing stemmed from the compromise of an NPM account belonging to a developer known as Kex.
A well-known developer, too.
Right. And once the attackers had that access, they went after the biggest, most widely used packages, stuff you install without even thinking about it. The bedrock of so many projects.
Yeah.
Can you give us a sense of the scale here? Which packages are we talking about?
Absolutely. And the list is genuinely shocking because these are so foundational. You've got Chalk, used for styling text in the terminal. Huge. Around 300 million weekly downloads.
Wow, 300 million.
Yeah.
Just for terminal colors.
Yep. Then strip NSI, essential for cleaning up strings with escape codes. That's about 261 million. Color convert, around 193 million. Color name, 191 million.
These are all related to text formatting and colors, mostly.
A lot of them, yeah. Then is core module, important for Node.js internals, that's 69 million. And our little friend ErrorX that kicked this whole thing off, still a hefty 47 million downloads a week.
47 million. Okay.
Yeah. Then Simple Swizzle at 26 million and has an Encino with about 12 million.
Wow. Just listing those numbers, it's like a who's who of basic JavaScript utilities. These aren't just libraries. They are, like our sources said, core building blocks.
Yeah.
Deeply embedded everywhere.
Exactly.
And when you add up those numbers, the combined weekly downloads, it exceeded 1 billion. 1 billion.
It's truly staggering potential impact.
Yeah.
And if we connect this to the, the bigger picture, This kind of attack really highlights the inherent trust we place, often blindly, in the open source ecosystem.
All right, we just npm install and assume it's okay.
We do. Developers, companies, everyone relies on these packages daily. They're often buried deep in the dependency tree, layers down. You don't scrutinize every line. So when a foundational layer like this gets compromised, the ripple effect is just immense, potentially affecting millions of users, applications globally. It's a stark reminder that even the smallest dependency, maybe maintained by just one person, can become this critical vulnerability. It puts entire systems at risk.
Okay, so we've tracked how it got in through that compromised Quicks account. We know it hit these massive packages. But once this malicious code, this crypto clipper, gets onto a system, what's its end game? What does it actually do? And what makes its methods, as you said, so surprisingly sophisticated?
Yeah.
Let's talk about that first attack vector, passive address swapping, the one that kicks in if there's no crypto wallet detected.
Right. That's the core of it. And it shows this really clever two-pronged approach. First, it does a little check. It looks for window.ethereum. That's the little flag that says, hey, is there a wallet extension like MetaMask active here?
Okay.
If it doesn't find one, it goes into this passive address swapping mode. And it essentially monkey patches your browser's core network functions, specifically fetch and XML HTTP requests.
Monkey patching. Okay, so it's actively rewriting parts of the browser's code on the fly to intercept all web traffic where crypto addresses might show up.
Precisely. It sits in the middle, and then it tries to swap addresses it finds.
But how does it do that without being, super obvious? Swapping my address for some random attacker address. I feel like I'd noticed that long string is different. Our eyes aren't that bad, are they?
Exactly, and that is the truly insidious part. This is where the sophistication really comes in. It doesn't just grab any random attacker address from its list. Oh no. The script contains these huge lists of attacker-owned wallets. Bitcoin, Ethereum, Solana, Tron, Litecoin, Bitcoin Cash. The works.
Okay, an arsenal of addresses.
But here's a kicker. It uses something called the Levenstein distance algorithm.
Levenstein distance. Okay, what does that do?
It's fascinating. It measures the edit distance, basically the visual similarity between two strings. So the malware looks at the legitimate address it intercepted, then searches its own list to find an attacker's address that is typographically closest, the one that looks the most similar to the real one.
Wait, so it finds an address that visually mimics the legitimate one?
Yes. It's engineering deception. It's designed to fool your eyes, exploiting the limits of our visual attention when we quickly scan those long addresses. It's not just swapping, it's swapping with a near-identical twin.
Wow, that's a chilling level of precision.
Yeah.
Making the swap almost impossible to spot visually. Okay, that exploits how quickly we skim information. But what happens if a wallet is detected? Does the clipper just give up?
Oh no. It becomes far more dangerous then. If it does find window.ethereum, meaning an active wallet, it activates its much more aggressive component, active transaction hijacking.
Active transaction hijacking. Sounds bad.
It is. This method directly patches the wallet's own communication methods, specifically functions like request and send.
So it's tampering with the wallet itself now.
Essentially, yes. So when you, the user, go to make a transaction, let's say an Etsy transaction, the malware intercepts that transaction data before it even gets sent to your wallet for you to sign and approve.
Before I even see the confirmation pop up.
Exactly. It then silently modifies the transaction details right there in memory. It replaces the legitimate recipient's address with a hard-coded attacker's address. Our sources even gave an example they found: 0xe484854EPO1D1B1D7697 BFB5C52F4C1 66976.
Okay.
Then that manipulated transaction with the attacker's address is forwarded to your wallet for your final approval.
So wait a minute. Even if I'm super careful and I meticulously check the address shown on my MetaMask confirmation screen, I could still be sending my funds to the attacker because the wallet itself was fed the wrong address by the malware.
Precisely. That's the terrifying part. If you don't, as the researchers put it, meticulously check the address on the confirmation screen, meaning you have to re-verify the address in the wallet pop-up against the address you intended to send to, perhaps from another source. If you just click confirm based on what the pop-up shows, your funds go straight to the attacker.
Wow. The code is actively working against you, making it look right until the very last second.
Exactly. It's a complete betrayal of trust right at that critical moment of approval. It's a really stark reminder of what can lie beneath the surface and how vital verification is, multiple times even.
Okay, this whole scenario just begs the question, what robust defenses do we even have against this level of digital impersonation and transaction hijacking, our sources pointed towards the Ethereum Name Service, or ENS, as maybe one potential shield, at least against some parts of this. For listeners maybe not familiar, ENS is basically a decentralized naming system on Ethereum. Lets you use human-readable names like yourname.eth instead of those long, complex addresses. It provides a layer of verifiable crypto-secure identity. So how could ENS actually help in a situation like this?
So ENS does offer a pretty powerful, though not complete, defense against the identity-based aspects like that address swapping. It shifts trust from just visually checking, which we saw as fallible, to actual verifiable identity.
How so?
Well, first, think about cryptographic identity verification. In wallets that support ENS well, like MetaMask or Rainbow, the UI often shows the at-depth name, not just the raw address, when you connect or transact. Now, if malware swaps the underlying address in the background, the ENS name resolution just wouldn't match the attacker's address. It would be obvious something's wrong.
Because the attacker doesn't own your name.f.
Exactly. They'd need your private key to control the ENS name itself, which is, basically impossible, hopefully.
Okay, that makes sense. What else?
Second, you have UI discrepancy detection. Imagine an infected app. The UI might say connected as user.eth, but if the malware is using a different address behind the scenes, a good wallet could detect that inconsistency. By doing its own check, resolving the ENS name, and seeing it doesn't match the address being used for the transaction, it could warn you.
So the wallet acts as a verifier.
Ideally, yes. Wallets often validate ENS during connection and signing, showing warnings if things don't line up. It turns impersonation into something detectable. And finally, there's protocol-level impersonation prevention. More dApps are starting to require connections based on verified.eth names. In those systems, if a transaction must target a specific .eth name, any attempt by malware to just jam in a raw attacker address would fail the on-chain validation.
Okay, that sounds like a pretty strong layer of protection, especially against tricking the user with similar-looking addresses. But you said ENS isn't a silver bullet, so where does it fall short? What are the gaps here? What can it do against this kind of attack?
Yeah, it's really crucial to understand the limitations. First, and this is key, ENS cannot prevent malicious code execution. It does absolutely nothing to stop that initial injection of obfuscated code, like from the compromised NPM package, from running in your browser or your build pipeline.
Right. The malware is already inside the house.
Exactly. So if that malware manages to steal sensitive data, like your seed phrase, before you even interact with a wallet UI or approve a transaction, ENS is totally irrelevant. ENS operates at the naming and identity layer, not the code execution layer.
Got it. US.
Second, its effectiveness really relies on implementation dependence. The protection only works if the dApps you use and the wallet you use robustly integrate and enforce ENS validation. If they don't do those checks consistently, or if the warnings aren't clear, users might still miss the discrepancies. It becomes mitigation, not prevention.
So it needs the whole ecosystem to adopt it properly.
Pretty much. And finally, think about the attack scope. This was a supply chain attack. It could easily affect backend servers, CI/CD pipelines, places where there's no wallet UI, no doth name being displayed to a user. In those environments, ENS plays absolutely no role.
Okay.
So yeah, while ENS is super important for fighting identity scams like swapping addresses in a UI, it doesn't stop the initial infection or exploits that happen behind the scenes.
Right. So, okay, let's bring this back to the practical side. What does all this mean for you, the listener, the learner, the developer, the user, just trying to operate safely online? How can we actually protect ourselves and our projects from this kind of sophisticated attack? What are the immediate, concrete steps people should be taking right now?
Our sources are very clear on this. The immediate action is audit your project's dependencies. Like right now.
Don't wait.
Don't wait. And the key tool you have is the overrides feature in your package.json file. This lets you basically force specific, known, safe versions of packages across your entire project. Even if some other dependency deep down is trying to pull in a vulnerable version, your overrides rule wins. It puts you back in control.
Okay, and just to give people a concrete example of what that looks like for these specific affected packages, you'd add an override section to your package.json, something like this, right? JSON name, your project version. 1.0.0 overrides chalk, 5.3.0 strip ANSI, 7.1.0 color convert, 2.0.1 color name, 1.1.4 is core module, 2.13.1 AirX, 1.3.2 has ANSI, 5.0.1 has ANSI, using those specific known good versions.
Exactly, those versions.
And after adding those overrides, what's the cleanup process?
Crucial step. delete your entire node modules folder. Get rid of it. And also delete your package-lock.json file. Start fresh, then run npm install again. That will generate a new, clean lock file based on your package.json, including those safe overrides, ensuring everything is pinned correctly.
Right. Clean slate locked versions.
Mm-hmm. And stepping back, this whole incident really underscores that the open source ecosystem, yeah, it thrives on trust. But that trust has to be combined with constant active vigilance. We can't just passively consume open source anymore.
We have to participate in securing it.
Exactly. Hardening CI/CD pipelines to catch weird anomalies, rigorously locking down dependencies to specific safe versions using tools like overrides, and just fostering a culture of security awareness across dev teams. These aren't optional anymore. They're non-negotiable for defending against these evolving supply chain threats. We really need to shift from passive trust to active verification in everything we build.
Yeah. This deep dive has really shown us how just a single line of obfuscated code or one compromised developer account can have these monumental implications across the entire digital world. Billions of downloads impacted. It's truly a reminder of how interconnected everything is.
Indeed. And the sheer sophistication here, using algorithms like Levenstein distance to deceive the human eye, it just highlights how attackers are innovating rapidly and relentlessly. And it leaves us with, I think, a provocative thought to consider. Beyond all these specific technical measures we've talked about, securing and using ENS, locking dependencies, how much of our digital security ultimately rests on our individual ability, our ability to meticulously verify things, to question our assumptions, and just to stay continuously informed in a world where so much is governed by unseen code affecting our digital lives, our assets.
Yeah.
It's a challenge that really extends beyond just developers. It touches the daily habits of every single digital citizen.
A powerful thought to definitely ponder as we navigate this complex and clearly ever-evolving digital landscape. Keep learning, keep verifying out there, and we'll see you next time on The Deep Dive.